Hello, everyone. My name is Kavan Adeshara. I'm a current sophomore majoring in computer science at Penn State University in USA. And today's topic that I would be discussing is face recognition using PCA integrated with Delaunay Triangulation. So, what is face recognition? Face recognition is a biometric user authentication method that identifies an individual based on his or her facial features. And most of you might be aware of what face recognition is because it's in high demand. It's employed in many devices, such as smartphones, surveillance cameras, etc. And some of you might even use face recognition to unlock your smartphone devices. Now, to approach the implementation of face recognition system, different approaches could be used, and there are many of them. Some of the primary examples are neural networks, PCA, support vector machines, Delaunay triangulation, Gabor wavelet, etc. So just to give a brief overview of what this research consists of. In this research, we investigate the integration of two different face recognition approaches. One is PCA and one is Delaunay triangulation. We're going to project face images, the training face images, onto the eigenspace and determine the Euclidean distances between the training images and one individual test images, and that would go for all the remaining test images. We will discuss that later in the slide with the PCA implementation, but for now, that's the brief overview of PCA. After doing PCA, we would acquire the average relative area of the face triangulation by Delaunay triangulation. Once we implement Delaunay triangulation and PCA, in the end, we would combine the above values together, acquired from average relative area and the Euclidean distance, and we would weigh both of those values equally. And for experimentation purposes, we would use Yale face dataset for training and testing purposes. And the purpose of this experiment is to test out the accuracy rate with different set of landmark points, and that will be also discussed in the later slides. So what is Delaunay triangulation? Delaunay triangulation refers to the triangulation of discrete set of points on a plane. And it does so in a manner that no point should be inside the circumcircle of any triangle. Figure 1 shows the representation of the concept, where you have 4 discrete points on the plane. A triangle is drawn taking into account 3 points. A circumcircle of that triangle is drawn, and it makes sure that no other point is within that circumcircle. And then it just keeps proceeding. And step 6, this figure right here, shows the final resultant triangulation from the 4 discrete points. Now, in face recognition, Delaunay triangulation is used to create triangular mesh of key face landmark points of a face. And those key landmark points could include the eyes, the nose, the mouth, the shape of the face, etc. And you could see the implementation of Delaunay triangulation in several social media ad filters, such as Snapchat, Instagram. And usually when you try to apply a filter on your face, a triangulation would appear, and that's just the system mapping out where your face is and where the key features of your face are. And then it would pop the filter according to that mapping. Okay, so let's talk about the implementation. So first we collected the training data set, and then we would convert all of those training images, face images, into vectors. Once we convert those, we located the face landmark point. Now, locating face landmark points could be done in several ways. One primary way is to use a neural network to train a landmark classifier class, which kind of takes in all the manual hand-drawn landmark points on different face images. And then once we locate those face landmark points, we would implement Delaunay triangulation on those face landmark points, and that was demonstrated in the previous slide. Figure 2 shows a sample landmark points of an image taken from the Yale face dataset. And figure 3 shows the triangulation of those phase landmark points, and that is the 68 landmark triangulation. We will be discussing 3 different landmarks and 3 different triangulation in the upcoming slides. So once we perform the line triangulation, we would obtain the set of vertices of all the triangles in the triangulation. That would help us find the edge lengths of all the triangles, and equation 1 shows that. After finding the edge lengths, we would obtain the areas of all the triangles from the provided edge lengths. And those areas could be calculated from equation 2. So once we acquired the areas, we would calculate the relative area of each triangular area. And that is just taking the max area in the set and then dividing each individual area from that max area, shown in equation 3. And then after we would acquire the average the relative area, we would obtain the average relative area of all the relative triangular areas. And that could be shown in equation 4. Once we do all of that, we would store the average relative area for later phase comparison. Okay, so in the previous slides, I did refer to the fact that we were going to integrate Delaunay triangulation and PCA. So what is PCA? PCA stands for Principal Component Analysis. It's a dimensionality reduction method that reduces the dimensionality of a large dataset into a small dataset in a way that the small dataset should contain enough information to represent the large dataset. It is used in all sorts of fields, medical, technological, etc., and is also used in face recognition. The purpose of it is to analyze large data and extract vital information, including getting rid of surplus information that does not really contribute to anything. In face recognition, PCA reduces the dimensions of the pixel value of an image, and it does so in a way that the compressed version of the image should contain ample information to represent the unique features of the original image. And usually when we implement PCA in face recognition, we provide face images in a grayscale format, black and white. So in terms of implementation, we establish a training data set. Then we would convert all of those training images into vectors. Figure 4 is not representative of all the images being used. Figure 4 is just like an example image. For this, we're going to use 135 images from the face dataset, and that will be discussed in the experimentation part. Once we convert all of those face images into vectors, we would find the mean image of all the image vectors, and that could be done so from equation 5. Figure 5 shows the mean phase of all the images from figure 4. And it's kind of like imposition of many images. After we do so, after we get the mean face image, we would subtract the mean face image from each individual image. And then we would perform singular value decomposition, SVD, to calculate eigenvalues and eigenvectors. That could be given from equation 7. Once we calculate those eigenvalues and eigenvectors, we would project the image vectors onto the eigenspace for k best eigenvalues. For this research, k was set to 25. And figure 6 just shows you an example like eigenfaces of all the images from figure 4. Once we project those images onto the eigenspace, we would store the information of those eigenfaces in the training database. And then for testing purposes, we would establish a testing data set, and we conducted the same process as we did for the training data set for PCA. And then in the end, we would store all the Euclidean distances of the testing images compared to training images for integration calculation. So let's talk about the crux of this research, which is PCA with Delaunay triangulation. There are a couple of things that I would like to mention. First, the program would perform Delaunay triangulation, and then it would perform PCA. The program would take the uncompressed version of an image for Delaunay triangulation, but then take the compressed version of an image for PCA to determine the Euclidean distance. In the end, the values we acquire from Delaunay triangulation and PCA would be added together. So as we could see, we would perform the Delaunay triangulation on the test image and acquire its average relative area. And then we would calculate the positive difference between the test and training image's average relative area. And then the positive difference that we get from subtracting test and training images average relative area, we would add that positive difference with the Euclidean distances that we acquired from PCA. And we do that in order to get the training image with the least Euclidean distance difference and average relative area difference. Now, in this experiment, we conducted 3 different trials of this experiment, taking into account different landmarks. So trial A was with 68 landmarks, trial B was with 79 landmarks, and trial C was with 194 landmarks. And figure 7 is just like illustrative of all the landmark points being used, and also the triangulation with it. As I mentioned before, we are using 135 frontal images from the face dataset, and they usually come in grayscale format, and there are several variant images for each individual in the database, and that could contain sleepy, happy, sad, wink, glasses, surprise, left light, right light, and normal. Here's a short demonstration.
Hello. This is a short demonstration of the program that integrates PCA with Delaunay triangulation. So I would run it. So in the background, it's doing all the visualizing, and then you would soon see the pictures of all the visualization. All right. So let's just arrange this first. Okay. This is okay. All right. So let's start off with this image. So I took this image, and this would happen with every test image and training images, but to just visualize the Delaunay triangulation, this is an example image. And as you could see, there are 3 different triangulation happening. There's a 68 landmark version, there's a 79 landmarks, and this is the 194 landmarks. Okay. All right. This is the 194 landmarks. Now in PCA, as you can see, this just for demonstration purposes, this is like a short, these are the collection of training images that we took from Yale face dataset for this demonstration. And as you can see from this collection, this is the mean face. That
I would like to mention one thing about this mean face image, and I think this is a very important information. So as you could see, compared to the mean face that I showed you in the PCA implementation, this has a lot of deviations. Because for this research, we were planning on using all the images aligned to the center. But then to test out like effective accuracy rates, we left the images unaltered. So that's why, if you could see in figure 4, not all the images are aligned in a straight line. And that's why you could see like heavy deviations in the mean image sector.
that kind of like superimposes each other image on one another. After that, those images, after subtracting the mean image with the individual image from the collection, you can project those images onto the eigenspace by performing SVD. and this is what it looks like this is what the images look like onto the eigenspace.
Okay. Okay, so about the results. Um, as I mentioned, we in the same experiment we conducted 3 trials using different landmark points. We compared the integration with traditional PCA to see if there were any improvement in accuracy rates. As you could see, PCA with the Delaunay triangulation with any landmark points is significantly better than using traditional PCA. And most notably, PCA with Delaunay triangulation using 194 landmarks yields better accuracy results than any other landmark points used in this experiment. And just to like give a brief of like the trials itself. So for the first trial, we have more training images and less testing images. In the second trial, we have close to like 50-50 amount of having the same training images, like close to a 50-50 amount of training images and testing images. And for the third trial, we had less training images, but then more testing images. And as you could see, PCA with Delaunay triangulation for 194 landmarks still yielded a pretty desirable accuracy rate. So, in conclusion, PCA, principal component analysis, implemented with any other technique, could help develop a robust face recognition system. And this research shows part of it. We implemented PCA with Delaunay triangulation, and it yielded better accuracy rates. And the integration, the PCA with Delaunay triangulation integration would be more effective with increased landmark points, as we could see from the result. And this system could be used in a plethora of different fields. A primary example could be the implementation of the system in an attendance marking system where we could clock in or clock out employees, or where we could mark a student present or absent. But with any other system, with any other approach, um, this face recognition system is not flawless. There are some areas that still need some work, and that can consist of further fine-tuning the landmark detection to detect the very intricate edges of your face. And that could account for this, like a slight change in expressions or a slight change in eyebrow raise, and that landmark that could be registered into the landmark detection. Also, another factor is to enhance the face recognition with lower image clarity. And this is like one of the main issues that we face to this day, that camera with lower image clarity are not able to fully recognize a face if there are drastic conditions that bugs down the image clarity. And also we could also implement face recognition from different side angles. Like, how would we recognize a face if there was like an overview of the face, or like if there was a side view of the face? And then lastly, and I think this is more relevant today, we could try to recognize people wearing masks with good accuracy. So one proposal could be that we would perform Delaunay triangulation on a face without mask, and then we would perform Delaunay triangulation with face Delaunay triangulation on face with the mask. So these are a couple of like future improvements that we could implement in the near future, and that would help develop an even robust face recognition system for everybody's convenience. Thank you.